Welcome to this problem walkthrough. Today, we're diving into LeetCode problem number 1728, Cat and Mouse 2. This is an exciting and challenging problem that involves simulating a strategic game on a grid between a cat and a mouse. We'll explore the problem requirements and step through the solution together. Let's get started. This problem involves a two-player game played on a rectangular grid. The players are a cat and a mouse, each starting from specific positions marked as C and M, respectively, on the grid. The objective of the game is for the mouse to either reach the food, represented by F, or avoid being caught by the cat, which happens if both players occupy the same cell. The grid also contains walls, represented by hashtag, which neither player can move through. On their turn, the mouse and cat can move left, right, up, or down to adjacent cells, but there are specific rules for movement. The mouse has the ability to move up to a certain number of cells, defined by mouse jump, in a single turn, but it cannot jump over walls. Similarly, the cat can move up to cat jump cells in a turn, with the same restriction. The game alternates turns, starting with the mouse, and ends under specific conditions that we'll explore further. The game can end in one of three ways. If the mouse reaches the food, the mouse wins. If the cat catches the mouse by occupying the same cell, the cat wins, or if the mouse is unable to reach the food, the cat wins by default. The challenge is to determine whether the mouse can win the game assuming both players make optimal moves. The problem takes three key inputs: the grid, which describes the layout of the game board, mouse jump, the maximum distance the mouse can travel in one turn, and cat jump, the maximum distance the cat can travel in one turn. The output is a Boolean value, true if the mouse can secure a win under optimal play, and false otherwise. Let's look at some examples to better understand how the rules play out. In the first example, the grid is a 4x5 setup where the food is located at the top right corner, the cat starts near the top, and the mouse begins near the center. The mouse jump is 1, meaning the mouse can only move one cell at a time, while the cat jump is 2, giving the cat greater range. Here, the output is true, indicating that the mouse can reach the food before the cat catches it. This happens because, even with optimal play from the cat, the mouse has a strategic path that guarantees it reaches the food safely. The walls in the grid help block certain approaches, allowing the mouse to outmaneuver the cat. In the second example, the grid is a single row where the cat starts between the mouse and the food. The mouse jump is 1, so the mouse can only move one step per turn, while the cat jump is 4, allowing the cat to cover large distances. The output here is false, meaning the cat wins. This is because the cat's superior jump range ensures it can intercept the mouse before it has any chance of reaching the food. Even if the mouse tries to move strategically, the cat's mobility gives it a decisive advantage. In the third example, the grid contains multiple rows and walls that create a more complex layout. The mouse starts in the bottom middle section, while the cat is above it, and the food is in the top right corner. Both players have equal jump ranges of 2 cells per turn. The output is false, as the walls create a scenario where the mouse cannot reach the food without being caught by the cat. These examples highlight how the interaction between the grid layout, jump ranges, and player strategies determines the outcome. Additionally, constraints and edge cases, such as small grids or blocked food, add further complexity to the problem, requiring careful analysis to determine the result. To solve the problem of determining whether the mouse can escape the cat on a grid, we need to simulate the game while adhering to its specific rules. The challenge lies in handling constraints like movement limits, obstacles, and alternating player turns. Initially, we might consider a brute force simulation, where every possible move for both the cat and the mouse is explored recursively. This involves alternating turns, simulating all potential game states. However, this approach quickly becomes infeasible for larger grids, as the number of possible states grows exponentially. The absence of optimization techniques like memoization makes this approach extraordinarily slow, especially for grids with thousands of cells. Alternatively, we could use backtracking combined with memoization to avoid redundant calculations by storing results of previously computed states. While this approach is more efficient than brute force, as it prevents revisiting the same state repeatedly, it still struggles with the sheer size of the state space, especially on large grids with many turns and possible moves to consider. Although memoization improves efficiency, the problem remains challenging due to the vast number of potential position and turn combinations. To address this, we turn to a dynamic programming approach that tracks multiple states simultaneously. Here, the problem is treated as a multi-state game involving the positions of the mouse and cat, whose turn it is, and the number of moves taken. Using a bottom-up approach, we calculate the results for each state starting from the terminal states situations where the mouse escapes, the cat catches the mouse, or the maximum number of moves is reached. This method is significantly more efficient, with a complexity of n*m*t, where n and m are the grid dimensions, and t is the maximum number of turns. However, implementing this solution requires careful attention to details like handling walls, respecting movement limits, and adhering to the turn-based rules of the game. While the approach is more complex to implement, it eliminates redundant exploration and systematically builds the solution. The dynamic programming strategy is chosen because it leverages the finite state space of the game, defined by the positions of the mouse and cat, the turn number, and the grid size. The game naturally concludes in terminal states, such as when the mouse escapes, the cat catches the mouse, or the maximum number of moves is reached. These terminal states act as the foundation for the DP solution. By working backward from these terminal states, we can determine the outcome for all possible game scenarios. This backward solving technique ensures correctness while avoiding unnecessary computations. Compared to brute force and memoized backtracking, this approach is far more practical for large grids, as it systematically explores all states without redundant calculations. The trade-off lies in the complexity of implementation and the additional memory required for the DP table, but these are manageable given the problem's constraints. The key insight that made this approach successful was recognizing that the game could be treated as a multi-state DP problem, with transitions governed by the game's rules. This understanding allowed us to efficiently compute outcomes across the entire state space. This problem, Cat and Mouse 2, is a fascinating challenge that involves two players, the cat and the mouse, competing on a grid. The mouse's objective is to reach the food before the cat can catch it, while the cat aims to catch the mouse. The grid itself is made up of walls that block movement, empty spaces where both players can move, the mouse's starting position, the cat's starting position, and the food. The game alternates turns between the two players, and the outcome depends on their movements. For example, the mouse can win either by reaching the food or by avoiding capture for the entire game duration. On the other hand, the cat wins if it manages to occupy the same cell as the mouse. To solve this problem, the first step is pre-processing the grid. This means parsing the grid to locate the starting positions of the mouse, the cat, and the food, and storing these positions for efficient reference during the simulation. Next, we define the game state, which is represented as a tuple containing the positions of the mouse and the cat, along with a turn indicator to specify whose move it is. This representation allows us to systematically analyze every possible scenario in the game. The game state is stored in a data structure, such as a dictionary or a 3D array, where each state is classified as a win, loss, or draw. To simulate the game, we use a breadth-first search, or BFS, approach. A queue is employed to explore the game states step by step, starting from the initial configuration. For each state, we generate all valid moves for the current player, ensuring that the moves stay within grid boundaries and avoid walls. Then, we evaluate the outcome of these moves. For instance, if it's the mouse's turn and it reaches the food, that state is immediately marked as a win for the mouse. Conversely, if the cat catches the mouse, that state is a win for the cat. If neither condition is met, we continue exploring subsequent states. Once terminal states, like the mouse reaching the food or the cat catching the mouse, are identified, we propagate the result of these states backward. This process, called backpropagation, ensures that earlier states are updated based on their connection to these outcomes. To improve efficiency, memoization is applied, where results of previously computed states are stored and reused. This eliminates redundant calculations, significantly speeding up the simulation. When handling edge cases, several scenarios need to be addressed. For example, if the grid is too small or the food is completely blocked by walls, it's impossible for the mouse to win. Similarly, if the cat starts in a position adjacent to the mouse, the cat wins immediately since it can catch the mouse in its first move. Another important scenario involves the maximum number of moves allowed. If this limit is reached, the mouse's ability to win can be constrained. Solving this problem involves applying game theory principles, where we evaluate all possible outcomes to determine the optimal strategy for the mouse. By reducing the game states through memoization, we avoid repeated calculations and make the algorithm more efficient. Additionally, if a guaranteed win or loss is discovered for either player, we can terminate further exploration of that state, further optimizing the process. The key data structures used include a queue for BFS, a hash map or 3D array for memoization, and a set to track visited states, preventing cycles. Together, these techniques allow us to systematically analyze the game and determine the outcome. The time complexity of this approach is proportional to the total number of possible game states, which depends on the grid dimensions, the maximum number of moves, and the number of valid transitions between states. This gives us a complexity bound of O, m*n** max _ moves, where m and n represent the grid's dimensions. Similarly, the space complexity is also O, m** n** max _ moves, due to the memory required for the BFS queue and the memoization structure. To illustrate, consider a grid where the mouse starts at the top left corner, the cat is positioned a few cells away, and the food is located near the bottom right corner. The mouse must navigate toward the food while avoiding the cat, and the cat will attempt to intercept the mouse. By simulating the moves alternately, we evaluate each game state to determine whether the mouse can reach the food or if the cat can catch it. Finally, the algorithm backpropagates the results, analyzing all possible scenarios to conclude whether the mouse has a winning strategy. If the mouse can escape to the food, the algorithm returns true, otherwise, it returns false. We start by importing the necessary modules and defining the solution class with the can_mouse_win function. The first step is to extract the dimensions of the grid and define the possible movement directions. We then identify the initial positions of the mouse, cat, and food by iterating through the grid. This is crucial because these positions will form the basis of our game logic. Next, we define a helper function, state_to_index, to convert a position and turn into a single state index, which will help us manage game states efficiently. To prepare for the game, we calculate the shortest distance from any cell to the food using breadth first search, BFS. We initialize a distance matrix with infinity for all cells, except the food cell itself, which is set to 0. A queue is used to process cells, starting from the food position. Using BFS, we process each cell in the queue and explore all possible movements in the 4 cardinal directions. For each direction, we calculate the new positions by taking steps up to the maximum of the cat's or mouse's jump distance. If a new position is out of bounds or blocked by a wall, we stop further exploration in that direction. For valid cells closer to the food, we update their distance and add them to the queue. After completing this BFS, we have a matrix indicating the shortest distance from each cell to the food. Next, we initialize the dynamic programming (DP) approach to evaluate game states. The maximum number of moves is derived from the grid size, and we use a dictionary to memoize results. The can_win function is then defined to recursively determine if the mouse can win from a given state. If the maximum moves are reached, the game ends in a draw, resulting in a loss for the mouse. In the can_win function, if it's the mouse's turn, we simulate all possible moves within its jump limit. For each move, we check if it leads to a winning state for the mouse. If the mouse reaches the food, it wins immediately. If no winning moves are found, the mouse loses this turn. On the other hand, if it's the cat's turn, we simulate all possible moves within the cat's jump limit. The cat wins if it captures the mouse or reaches the food first. The recursion evaluates each scenario and memoizes the result to avoid redundant computations. The alternating turns, combined with the recursive checks, ensure that all game possibilities are explored while optimizing performance through memoization. Finally, the can_mouse_win function returns the result of the can_win function, starting with the initial positions of the mouse and cat, and the turn set to 0, indicating the mouse's turn. This completes the implementation, allowing us to determine whether the mouse can win given the grid layout, jump constraints, and starting positions. By combining BFS for pre-computing distances and dynamic programming for game state evaluation, this solution effectively handles the complexity of the problem. To implement the solution in Java, we start by defining the solution class and the method can_mouse_win. This method takes the game grid, the cat's jump distance, and the mouse's jump distance as input parameters. We first calculate the number of rows and columns in the grid, and define the possible movement directions for the cat and mouse. Next, we locate the initial positions of the mouse, cat, and food within the grid. These positions are identified by iterating through each cell of the grid and checking for the characters M, C, and F, respectively. Once these positions are found, we initialize a distance-to-food matrix to keep track of the shortest distances from each cell to the food. To populate this matrix, we use a breadth-first search starting from the food's position. A queue is used to traverse the grid, and as we process each cell, we calculate the distance for adjacent cells based on the maximum possible jump distance of the cat or mouse. The breadth-first search continues by iterating through each possible direction and step size. For every valid move, we calculate the new row NX in column New York. If the new position is out of bounds, encounters a wall, represented by hashtag, or has already been reached with a shorter or equal distance, we skip further processing for that path. Otherwise, we update the distance-to-food matrix with the new shortest distance and add the position to the queue for further exploration. After computing these distances, we prepare for the recursive part of the solution by defining a memoization map to store intermediate results and avoid redundant calculations. We also calculate the maximum number of moves, which is a function of the grid size. Finally, we call the recursive helper method canMouseWin, passing the initial positions of the mouse and cat, the turn indicator, the current move count, and other parameters necessary for the game logic. In the recursive method canMouseWin, we first check for base cases. If the maximum number of moves has been reached, the game results in a draw, so we return false. We also encode the current state of the game as a string to check if the result for this state is already memoized. If so, we return the stored value. The next base cases handle win or loss conditions. If the mouse reaches the food, it wins, and if the cat reaches the food or the mouse, the cat wins. The logic then branches based on whose turn it is. If it's the mouse's turn, we initialize the result to false, indicating the mouse hasn't yet found a winning path. We explore all possible moves the mouse can make, constrained by its jump distance and the grid's boundaries. For each valid move, we recursively call canMouseWin with the updated positions in turn. If the mouse finds a move that guarantees a win, we update the result to true and stop further exploration. If it's the cat's turn, the logic is similar but reversed. The cat tries to prevent the mouse from winning, so we start by assuming the result is true, meaning the mouse can't win. Then, we explore all valid moves the cat can make within its jump distance. For each potential move, we recursively check if the mouse can still win after the cat's move. If the mouse can secure a win from any of these positions, the result is updated to false, and the cat stops exploring further. This minimizes the cat's chances of losing. Once all moves for the current state are evaluated, we store the result in the memoization map to avoid recalculating it later. Finally, we return the result, which determines whether the mouse can win given the current positions in turn. This completes the implementation of the recursive solution, leveraging both dynamic programming and game theory principles. To start with example 1, we have a simple one-row grid where the mouse begins at position 0, 0, the cat starts at position 0, 2, and the food is located at 0, 4. The grid dimensions are 1 row and 5 columns. Using breadth-first search, we calculate the distance from the food to all other cells in the grid. The food itself has a distance of 0, and moving leftwards, we find that the cell at 0, 3 is 1 step away, 0, 2 is 2 steps, 0, 1 is 3 steps, and finally, 0, 0 is 4 steps away. This gives us the baseline understanding of how far each entity is from the food and sets the stage for the turn-by-turn simulation. In the first turn, the mouse goes first and moves to position 0, 1. This is a valid move because the cat's distance to the mouse's new position is still greater than the mouse's distance to the food, meaning the mouse has a chance to progress. On the second turn, the cat moves to position 0, 3, strategically getting closer to the food. Then, on the third turn, the mouse attempts to move to position 0, 2, but this is where the game ends. The cat catches the mouse at this position, resulting in a loss for the mouse. This example demonstrates how the cat's ability to intercept the mouse can lead to the mouse losing if it cannot outmaneuver the cat. Now, in example 2, we have a slightly longer grid with 6 columns, where the mouse starts at position 0, 0, the cat starts at position 0, 5, and the food is located at 0, 4. Calculating distances from the food using BFS, we find that the food itself has a distance of 0, the cell at 0, 3 is 1 step away, 0, 2 is 2 steps, 0, 1 is 3 steps, and finally, 0, 0 is 4 steps away. On turn 0, the mouse uses its higher jump range to move directly to position 0, 4, reaching the food before the cat has a chance to intervene. This results in a win for the mouse, showing how the mouse's jump range can sometimes allow it to reach the food unchallenged. In example 3, the grid becomes more complex with obstacles represented by hashtag. The mouse starts at 0, 0, the cat is at 2, 0, and the food is located at 1, 3. Using BFS, we calculate distances to the food for all reachable cells, considering the constraints of the obstacles. On the first turn, the mouse moves to position 1, 0, taking a step closer to the food while staying out of the cat's immediate reach. On the next turn, the cat moves closer to the mouse's position, creating additional pressure. However, the mouse carefully chooses its subsequent moves to avoid the cat while progressing toward the food. Ultimately, the mouse reaches position 1, 3, securing a win. This example highlights the importance of strategic movement and how the mouse can navigate around obstacles in the cat's pursuit to achieve victory. Summarizing all examples, the outcomes are example 1 false, example 2 true, and example 3 true, reflecting the dynamic interplay of distances, obstacles, and strategic decision-making in the game. The time complexity of the solution is influenced by two main factors. First, we have the breadth-first search, or BFS, which is used to calculate the shortest distance from every cell on the grid to the food. This process involves traversing all reachable cells starting from the food's position. Each cell is processed just once, and for every cell, we evaluate up to max, cat jump, mouse jump, steps in each of the 4 possible directions. On a grid with rows and calls, this results in a time complexity of approximately O, rows asterisk calls asterisk max, cat jump, mouse jump. This term represents the cost of pre-computing the distances to the food, which is an important foundation for the rest of the solution. The second component of the time complexity comes from the dynamic programming solution, which involves recursive calls within the can_win function. Here, each game state is uniquely defined by the positions of the mouse, the cat, and the current turn. Since the mouse and cat positions can span O, rows asterisk calls, each, and there are 2 possible turns, the total number of states is O, rows (2 asterisk calls (2). For each state, the mouse or cat can explore up to 4 directions, taking up to mouse jump or cat jump steps, which means there are O, max, mouse jump, cat jump, asterisk 4, recursive calls per state. Combining these factors, the dynamic programming solution has a total complexity of O, rows (2 asterisk calls (2 asterisk max, mouse jump, cat jump, asterisk 4). When we combine this with the BFS component, the overall time complexity is O, rows asterisk calls asterisk max, cat jump, mouse jump, plus rows (2 asterisk calls (2 asterisk max, mouse jump, cat jump, asterisk 4). However, in practice, the BFS term is much smaller, so the dominant time complexity is O, rows (2 asterisk calls (2 asterisk max, mouse jump, cat jump). Now let's consider the space complexity of the solution. There are 3 main components to account for. First, the BFS storage uses an array, distance_to_food, to store the shortest distance to the food for each cell, which takes up O, rows asterisk calls, space. Additionally, the BFS queue can store up to O, rows asterisk calls, cells in the worst case, so the total space for BFS is O, rows asterisk calls. Second, the dynamic programming solution relies on a dictionary, DP, to store the results of all evaluated states. Since each state corresponds to a unique combination of mouse position, cat position, and turn, the total number of states is O, rows (2 asterisk calls (2). Each state requires O1 space, so the total storage for the DP dictionary is also O, rows (2 asterisk calls (2). Finally, the recursive call stack can go as deep as max_moves, which is proportional to O, rows asterisk calls, with each call requiring O1 space. Therefore, the total call stack space is O, rows asterisk calls. When we combine these components, the overall space complexity becomes O, rows asterisk calls plus rows (2 asterisk calls (2). Since the space required for the DP dictionary dominates, the final space complexity is O, rows (2 asterisk calls (2). To put this in perspective, let's compare this optimized solution to a naive brute force approach. A brute force method would simulate every possible game path by trying all possible moves for both the mouse and the cat at each step. Given that the maximum number of moves is O, rows asterisk calls, the total number of game paths in a brute force solution would be exponential, specifically O, max, mouse jump, cat jump, asterisk 4, caret max underscore moves. This exponential complexity makes the brute force approach infeasible for larger grids. In contrast, the optimized dynamic programming solution evaluates a polynomial number of distinct game states and avoids redundant calculations, transforming the problem from exponential to polynomial complexity. Finally, let's summarize the best, average, and worst-case scenarios. In the best case, the mouse or cat reaches the food within the first few moves, causing the recursion to terminate early. Here, the time complexity is closer to O, rows asterisk calls asterisk max, cat jump, mouse jump, where the BFS dominates. However, in the average and worst cases, all possible game states are evaluated, resulting in a time complexity of O, rows caret 2 asterisk calls caret 2 asterisk max, mouse jump, cat jump, where dynamic programming dominates. To conclude, the final time complexity of the solution is O, rows caret 2 asterisk calls caret 2 asterisk max, mouse jump, cat jump, and the space complexity is O, rows caret 2 asterisk calls caret 2. This demonstrates how the optimized approach balances efficiency and scalability, making the solution far more manageable for larger grids and more complex scenarios. When tackling this problem, there are a few common pitfalls to watch out for. One major issue is ignoring edge cases. For instance, consider grids where the mouse has no escape path, the cat starts adjacent to the mouse, or all food is unreachable. These scenarios can easily lead to incorrect results if they're not explicitly addressed in your logic. A good practice is to test your solution on small grids, extreme starting positions, and situations where reaching the goal is impossible. Another common mistake is misunderstanding the turn rules. Remember, the mouse always moves first, followed by the cat, and this alternation must be strictly adhered to. Failing to model this properly can lead to critical logic errors. Finally, overlooking the maximum move limit specified in the problem can result in infinite recursion or loops. To prevent this, include a counter to track moves and terminate the game appropriately when the limit is reached. Another frequent mistake is not considering all possible moves for both players. Each player has 5 options: moving up, down, left, right, or staying in place. Missing the stay in place option can lead to incomplete solutions and missed opportunities for either player. To handle this, ensure your implementation accounts for all 5 possibilities. Inefficient state representation is another challenge. For example, failing to include key details like the current turn or move count can result in redundant computations and even time limit exceeded errors. To improve efficiency, represent the state using a tuple or similar structure. A common choice is mouse underscore position, cat underscore position, turn, move underscore count, which allows you to leverage memoization effectively and avoid unnecessary recalculations. When preparing for interviews, it's crucial to focus on clear state space modeling. Define the game state comprehensively, including positions of the mouse and cat, the current turn, and the move limits. This clarity is essential for solving complex game theory problems. Dynamic programming with memoization is another key technique. By storing results for previously encountered states, you can avoid redundant computations and manage the problem's high branching factor more efficiently. It's also important to understand the objective thoroughly. For the mouse, a win means reaching the food, while for the cat, it's either capturing the mouse or preventing its escape. Identifying early termination conditions based on these objectives can significantly enhance your solution's performance. Finally, practicing similar two-player game problems will deepen your understanding of concepts like minimax, alpha-beta pruning, and backward induction, which are often applicable to challenges of this nature. If you're looking for related problems to expand your understanding, there are several on LeetCode worth exploring. Problem 913, Cat and Mouse, is a simpler version of this problem with a more straightforward graph structure. Problem 1905, Count Sub-Islands, focuses on grid-based traversal and connectivity, which aligns with the movement mechanics in this challenge. Problem 847, Shortest Path Visiting All Nodes, is another graph-based problem with an emphasis on state representation and optimization, similar to what's required here. Lastly, problem 1293, shortest path in a grid with obstacles elimination, involves grid traversal with additional constraints, requiring careful management of states and transitions. These problems can help you build a stronger foundation for tackling complex scenarios like cat and mouse 2. There are several approaches you can consider when solving this problem, each with its own trade-offs. A brute force approach using depth-first search explores all possible moves for the mouse and the cat recursively. While simple to implement, it's computationally expensive and prone to time limit exceeded errors on larger grids. Breadth-first search with state tracking is another option. By exploring states level by level, BFS can be more efficient than DFS in finding the shortest path, but it may require significant memory for queue storage. A more strategic method involves using minimax with pruning. This evaluates the best moves for both players and can incorporate alpha-beta pruning to reduce the search space. However, while theoretically strong, this approach can be complex to implement under tight time constraints. Finally, dynamic programming with memoization is often the most efficient. By storing results for previously computed states, you avoid redundant calculations, but it demands careful attention to state representation and transition logic to ensure correctness. Great job making it to the end. In this walkthrough, we tackled LeetCode problem number 1728, Cat and Mouse 2, and explored how to solve it step by step. We covered grid-based game simulations, state modeling, and key takeaways for applying this approach to other problems. Thank you for tuning in, and be sure to like, share, and subscribe for more problem-solving insights. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!